Hi, this is Ari Everett. This is for group Beluga Dogs. We got together in lieu of the lab cancellation to do this. So here is our work. This is Logicin that we built task A, B, and C into. This is all of it, conceptual and standard circuits. Let's blow this up to explain it further. So in the top left here, we have task A's adder conceptual. This is right from the lab handout, but we wanted to write it down to just get the brainstorming going. So let's poke in B, which is the carry in adding from what is an A. So we can see the input to the output. Let's put in a bigger number there, 0011. Carry in or adding of 1 brings it to 0100. And then task A for the actual circuit was to create a circuit that had a 4-bit input with a selection switch that allowed us to give either the ones or twos complement. The assumption here that is really important is that the input A0 through A1 is already complemented. So if we put in a number of 0011, it would be 0011 already. Selection switch here is set to the carry in. That's similar to the concept here where the carry in to the least significant bit is added, just 1 bit, which is what gets you from ones complement to twos complement. From standard unsigned to ones complement, you flip all the digits to the opposite symbol, 1 to 0, 0 to 1. And for twos, you add the 1. So here we can see 1, 1, 0, 0, you add a 1, it equals 0, 1, 0, 0. When you goes 1, 1, 0, 1, and you don't add anything, well, that is the ones complement. So that is 0, 0, 1, 0. And again, ones complement is flipped. So 1, 1, 0, 1 flipped is 0, 0, 1, 0. The output is 0, 0, 1, 0. You add a 1, that goes to 0, 0, 1, 1. For task B, this subset, we took the standard input. It is assumed not complemented. So let's input 0, 1, 0, 0. We use this negation method to show an output of either no change to the input or the sign magnitude. And we know that sign magnitude in 4-bit input means that the most significant bit is the sign, 0 and 1, and the magnitude, which is the remaining 3 digits. So we took it a little bit further than the handout in the conceptual side here. Instead of making 1 pin with 4 digits, we made 4 separate pins. This helped us conceptualize what it was going to be in the latter portion when we built out the full circuit. So on the most significant bit, this is the important part, is we input that into an XOR along with the selector. This acts as a switch with the XOR logic. So whichever one is high, it will output that number. And if they're both high, it will not change at all. So let's change it to here, 1 and 1, and it's 0. So what that does is 1, 1, 0, 0 is the input. So the output number, which the switch is on to say, yes, do the sign magnitude conversion of this, is 0, 1, 0, 0. For task C, we have a 4 options mux circuit here where we copied and pasted the previous circuits and did some trial and error and some conceptualization during the design process in order to get this here. The important remarks are this. S0 essentially chooses between the subgroups a sort of nested if statement in the programming world for this hardware. So it's choosing here, you can see it runs and branches out to the XOR, which is task B, and then branches out to the end of task A, which is the 74283 adder from task 1. So it's essentially choosing between the 2 subgroups being task 1 and task 2. And then S1 is plugged in. It's through a NOT gate here to make it active low, the way we routed this in the A and B in the final IC here. But this is essentially choosing at the top line the first of the nested if statements. Once the selection of the nested if is created, then it goes on and does the final selection of the selection that was previously made here in the final chip and then outputs that. So for example, let's do positive 6 base 10, which in 4-bit binary is 0, 1, 1, 0. And let's go through the 4 tests. Okay, I've got my notes here. 0, 0 is no change. So 0, 1, 1, 0 outputs 0, 1, 1, 0. 0, 1 should negate the input in sign not magnitude form. 0, 1 meaning 0 in S1 and 1 in S0. So that switches our subgroup here. And that is indeed correct because it adds flips the 0 to the 1. Let's go S1, 1, and S0 at 0, which should send it through the ones complement form. So without even looking to the right, I should know it's 1, 0, 0, 1. And that's indeed correct, 1, 0, 0, 1. And then 1, 1 on both switches will send it through the twos complement. So without looking, we add 1 to this. It should be 0, 1, 1, 1, or you can do the shortcut starting from the original number. From the least significant bit to the first one, it stays the same. Then you flip the rest. So it's 1, 0, 1, 0, and that's indeed 1, 0, 1, 0. And I'm sorry, I miscommunicated. Adding 1 would to it, I meant that for adding 1 to the 1's complement, which would get you the 2's complement. So if we go back here to 1, 0, 1, 0, 0, 1, you add 1 to that would equal 1, 0, 1, 0. And that's our circuits. Thank you.